Hello everyone, I welcome all of you on behalf of SemExcel. In AQ semester examinations, generally 40% questions are asked from the previous year questions. So here we will discuss all the previous year questions conceptually one by one. We will start from 2K19 questions and we will solve all questions year by year subject wise. So let's start without wasting any further time. The first subject that we will discuss is Mechanics of Solid of year 2K19. The question is the ratio of modulus of rigidity, that is represented as G, and modulus of elasticity, that is represented as E, for most of the material. To solve that question, we have to know certain relations. That is E is equal to 2G into 1 plus mu and E is equal to 3K into 1 minus 2 mu. The first question can be solved using only the first formula. Here G by E will be equal to 1 by 2 into 1 plus mu. For most of the material, this mu is in between 0 to 0.5. So this G by E will be equal to less than 0.5. Hence G by E is equal to 1 by 2 into 1 point something. So this value will be less than 0.5. Hence option 3 is the correct answer. Now I will discuss some of the concepts. This question can be asked in many ways and you can answer all the questions using some formulae. Here is the sum formulae. E is equal to 2G into 1 plus mu. Here mu is known as the Poisson's ratio. Its value is in between 0 to 0.5 for most of the engineering materials. The other formula is E is equal to 3K into 1 minus 2 mu. This K is known as the bulk modulus. Again, if you use the first and second formula, we will get another formula that is equal to E is equal to 9 kg divided by 3K plus G. Using only these three formula, you can answer all of questions of this type. So please note down this formula. It will help in your semester exams. We will move further for the next question. Here, the question is the temperature stress is a function of, these are given options. First, we will discuss what is the temperature stress. Suppose we have one material of length L and alpha is the coefficient of thermal expansion and E is the modulus of velocity and delta T is the change in temperature. Then the strain is defined as alpha into delta T, and from the Hooke's law we know that stress is directly proportional to the strain, or stress is equal to Young's modulus of velocity into strain. This strain is represented by a symbol epsilon. So putting this value here, we get stress is equal to E into alpha into T. We should better write delta T here. Now this question can be answered. The stress depending on the E, that is the modulus of velocity, alpha, that is the coefficient of thermal expansion, and delta T, that is the change in temperature. So all three options are correct, hence option 4, all of the above is correct. Let's move to the next question. The question is normal stress on a plane, the normal to which is inclined at an angle theta with the line of action of uniaxial stress this should be sigma, right? Sigma theta is given by. For that, let's say we have one element. Here is the theta, this is the stress. So we have another plane. So in question it has been asked what is the sigma at angle theta. We'll use this formula. Sigma at an angle theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Please note, in question only normal stress is given. There is no shear stress, so here tau xy is equal to 0. In question there is only one component of stress, that is the sigma is equal to sigma x. There is no y component, that is the sigma y. So here sigma y is also be 0. So sigma theta is equal to sigma x by 2 plus sigma x by 2 into cos 2 theta. Let's take sigma x by 2 common, you will get 1 plus cos 2 theta. Sigma x by 2, this term will be equal to the cos square theta. Cos square theta, 2 cos square theta. This 2 and 2 will get cancelled out and we will left off only with the sigma x cos square theta. So option 2 will be the correct option, sigma cos square theta. The concept here is you should remember this formula and use this formula whenever it is required. Let's move to the next question. In Mohr circle, the radius gives the value of, means in Mohr circle, what is this radius? Let's say we have one element. There is sigma x here, sigma y here, and tau xy is acting on the surface. For this, the Mohr circle can be drawn as this one. This is the Mohr circle. Here we have sigma x, value this one, sigma x and tau xy. Then we have other sigma y and tau xy. Right. This is the maximum stress. This one is known as the major principal stress, sigma 1. This minimum stress is known as the minor principal stress, that is the sigma 2. Here, this radius, what is this radius, is known. Here you should remember one formula, that is the sigma 1 major or 2 minor stress is equal to sigma 1 plus sigma 2 by 2 plus for major stress minus for minor stress into sigma x minus sigma 2 by 2 whole square plus tau xy square. This tau xy represents the radius and this represents, we can write it as sigma x and sigma y. This represents the center line of this. So what we can say about this radius? This is equal to this and this term is known as the maximum shear stress. So option 4 will be the correct option, maximum shear stress. Please remember this formula. The same question can be asked like this: calculate the major principal stress and minor principal stress if sigma x and sigma y are given. Right. Next question. Variation of shear force in the cantilever carrying load of the intensity of which varies uniformly from 0 at very end to W per unit run at the fixed end is given by. This question can be represented as like this. We have 0 load at the free end and we have W load at the end of the cantilever beam. Now what is the shear force? Shear force is the total load acting on a section either from the left side or from the right side. So shear force on a section X can be represented as area of this load. So the Y, or let's say there is a section X, so this ordinate can be written as W by, suppose this length is L, W by L into X, and area is equal to shear force at X will be equal to half into base length into height to X. It will equal to 1 by 2L Wx square, right? So here we are getting the parabolic variation. So option B is the correct option, that parabolic law will be there. Now in transversely loaded beam, the maximum tensile stress occurs at whether the bottom of the edge or top of the edge or neutral axis or where. So in first case, let us consider the simply supported beam. Now for any loading condition, deflection pattern would be like this. So there will be compression at the top and tension at the bottom. The second case is for the cantilever beam. If there is a load, transverse load, then deflection will be like this. So there will be tension at the top here and the compression at the bottom here. So this question is not fully right. In this question, they should mention that he is talking about which type of beam, whether the simply supported beam or the cantilever beam. If in question it is given that it is a simply supported beam, then bottom edge will be correct answer. And if he is talking about the cantilever beam, then top edge should be the correct answer. This is not the correct answer. Now the next question is maximum deflection for a simply supported beam at the center point load is equal to, let's say we have a simply supported beam and we have a point load at the midpoint W. Then this deflection, midpoint deflection delta, this delta is given as WLQ by 48 EI. Please remember this formula. So option 4 is the correct option. Here I would like to give some more formula. The first is this one, simply supported beam with point load at the center. This delta is equal to WL4 by 48 EI. And again the slope at the end point, this theta is given as WLQ by 16 EI. Please note that we have LQ at this point and 16 at the bottom. The second is, if we have a cantilever beam and we have a point load at the tip W, then in this case delta is equal to WLQ by 6 EI. Again, if we have a UDL load W, then delta is equal to WL4 by 8 EI. Here theta is equal to WL square by 2 EI. Here theta is equal to WLQ by 6 EI. Here it should be WLQ by 3 EI. Now the most important thing, the fourth point. If we have both end fixed and a point load in between W, then in this case the deflection is 1 by 4th of that we get in case of simply supported beam. And if we have a UDL load, in that case the deflection is 1/5 of, we get that in simply supported beam. We have not discussed this loading. Here delta is equal to 5/384 WL4 by EI. Here this is the W kilonewton per meter. So please remember this formula. We will move forward for the next question. Maximum deflection of a fixed beam. Please note, here is a fixed beam carrying UDL load is. Again, we have discussed in the last slide that this is this case, right? So this is the given fixed beam. We have a UDL all over, and the deflection delta max is being asked. We have told that this deflection is equal to 1/5 of deflection of simply supported beam. That is equal to 1/5 of, this is given as 5/384 WL4 by EI. 5 get cancelled out, and we will left with WL4 by 384 EI. So fourth option is the correct option. Let's move to the next question. When a shaft is subjected to a twisting moment, every cross section of the shaft will be under. We have 4 options given. Let's say we have a shaft. This is the shaft that we have. This is fixed here, and this is the other end. Here is a twisting moment. Then in that case, everywhere all the cross section area will be under shear stress. If there has been a axial load P, then this shaft will be under the tensile stress. If the direction of the load is in opposite direction, then there have been a compressive stress. But if there is only twisting moment, then we have shear stress. So third option will be the correct option. Next questions. The product of tensile force on the shaft and the radius of the shaft is known as. This is the same question. Let's say we have a shaft. It is a fixed on a wall, and there is a tensile force that is equal to this. Here is a tangent, this is a force T, then this force, so let's say this force is F. This force F into this radial distance R. This is known as the torque, or this is also known as the twisting moment. So second option is correct option, twisting option. Here we come at the end of the first lecture. The next question will be discussed in the next video. I thank all of you for your patience, and SemExcel team for writing questions on the slide. Thank you very much.